Shane Lechler punts a football at 65-degree angle relative to the horizontal with an initial velocity of 25 meters per second. So we're going to have to break that 25 meters per second into its components, the horizontal component Vx and the vertical component V0, the initial velocity. So we're going to go ahead and draw the picture. I've got the football. It's going up to the right at 25 meters per second, 65-degree angle from the horizontal or from the horizon. Make sure your calculator is in degree mode. The Vx horizontal is going to be calculated as 25 cosine 65. Cosine because it's adjacent to the angle. On the opposite side, we use sine, where we're going to use 25 sine 65. So hypotenuse, function, angle for each. The hypotenuse, function, then the angle. Since it's moving in 2 dimensions, I'm always going to do a t-table for x and y. I go ahead and write in the variables, and I just get ready. Don't know how much I'm going to need of it, but it helps me isolate what I know and organize my variables and my thoughts. A asks us to calculate the hang time of the punt. The hang time of the punt is how long it's in the air, total time in the air. So right now I'm just putting in my Vx for my calculation above, 25 cosine 65. And then 25 sine 65. And that Vx is 10.57, and then the V0 is 22.66. For the hang time, the total time in the air, we know we're going to use an acceleration of -10 because the initial velocity is up being positive, the initial direction of motion. Acceleration coming from gravity is downward, so it's going to be -10. And the final velocity is returning to its original position. The final velocity is -22.66. It's going to have the same velocity at the same position in space, but it's going to be in the opposite direction. It's now moving downward. We're looking for time. And if we know the initial velocity, the final velocity, the acceleration, and we're looking for time, those 4 variables, we're going to utilize the Votad equation. V is equal to V0 plus acceleration times time. If we want to rearrange for time, we're going to subtract V0 from both sides, and we get V minus V0 is equal to A times T. Divide both sides by A, and we get V minus V0 over A is equal to T. Putting in the values that we know, -22.66 minus 22.66 divided by -10 is equal to our time. So what would that be, like 45.32, something like that, divided by 10. So 4.532 seconds would be our time. Yeah, it looks like that's the way it's going to calculate out. Calculate the horizontal distance the ball travels before striking the ground. Here it's asking us for delta x. Delta x is calculated as velocity in the x direction times time. Well, we just got time that's going to be in the air, 4.532, and the velocity in the x we said was 10.57. So we take our 10.57 from our table and multiply by the total time in the air. .66 meters would be our horizontal displacement. Calculate the maximum height of the punt. The maximum height of the punt, what do we know about that? Well, we know it's going up at positive 22.66 meters per second with an acceleration down -10 meters per second square. At that highest point, what do we know? We know that the final velocity goes to 0. Vertical velocity is 0. So if the final vertical velocity at the maximum height is 0, and the initial is 22.66, and acceleration is -10, we're solving for delta y. Those variables lend us to use the v square is equal to v0 square plus 2a delta y. Subtract both sides by v0 squared, and then divide both sides by 2a, and you get v squared minus v0 squared over 2a is equal to delta y. It's ready for us to solve. We would have 0 squared minus 22.66 squared over 2 times negative 10. So at the top we should get a negative 513.48 divided by negative 20. And our final answer would be 25.67 meters. Okay, new question, number 2. A cannon is fired with an initial velocity of 135 meters per second at an angle of 30 degrees relative to the ground and lands at the same height as it was fired from. So we're going to be shooting it off up and to the right at 135 meters per second. The angle is 30 degrees as compared to the horizontal or the ground. We're going to break it into its components so that we know what the horizontal velocity is and the initial vertical velocity. The horizontal velocity, because it's adjacent to the angle, we're going to use the hypotenuse. The function we're going to use is cosine and then the angle. So 135 cosine 30 in degree mode of your calculator. The initial vertical velocity would be 135 sine 30. Once we calculate those, we're going to put those values into the table, the XY table, and then we never have to look at the angles again. We're only going to break them into their components, put those values into the table, and then everything is the way it has been. So I still make my XY table, delta x, Vx in time, and then on the right I would have delta y, V naught, V, acceleration in time. The first question asks us to find the maximum height of the cannonball. At the maximum height of the cannonball, we know that the vertical velocity would be 0. If the initial velocity is 67.5, the acceleration's in the opposite direction, so negative 10, and for this portion of the projectile flight, the final velocity is 0, and we're looking for delta y. This lends us to the same equation we were using before. V squared is equal to V naught squared plus 2a delta y. We've already rearranged it once, where we've got V squared minus V naught squared over 2a is delta y. That rearrangement was done in number 1, letter C. And then we can plug in our numbers. We would have 0 squared, or 0, minus whatever 67.5 squared is, over 2 times negative 10. 67.5 squared. So at the top we would have negative 4,556.25, and then we're going to divide that by negative 20. So we should come up with a number close to 227.81. And this is meters because it's the displacement in the y. Find the horizontal distance the cannonball landed from the cannon. For the horizontal distance, what are the things that we know horizontally? In order to calculate horizontal, we know delta x is Vx times t. We need time. We have Vx, but we need Vx times t to get delta x. So let's solve for time then. Total time in the air. Well, we know the initial velocity is 67.5 upwards and positive. The final velocity right before it hits the ground would be, since it's the same height, would be negative 67.5 meters per second. And the acceleration is down negative 10 meters per second square. If we were to use the VOTAT equation, we could solve for time. I'm just going to subtract V naught from both sides. I get V minus V naught is equal to A times T, and then divide A on both sides. That gives us V minus V naught over acceleration is equal to time. V is negative 67.5, and then we're going to subtract V naught 67.5 and divide that by negative 10. So that should be 135 divided by 10, or 13.5 seconds. So now we know how long the cannonball is in the air. It's in the air for 13.5. The horizontal velocity doesn't change, so we're just going to say delta x is equal to Vx times t. Vx is, again, coming from that 135 cosine 30, or 116.91 times 13.5. And then 116.91 times 13.5 gives us 1,578.29 meters. Brings us to number 3. A motorcycle stuntman launches himself from a ramp at an initial velocity of 56 meters per second. The ramp is inclined at an angle of 35 degrees relative to the horizontal. So we need to draw the picture so we can see what's going on. He's being launched at 56 meters per second up and to the right. He's at a 35 degree angle to the horizontal. We're going to break his 56 meters per second velocity into its components. The horizontal component, Vx, coming from 56 cosine 35, and V naught, the initial vertical velocity, going up at 56 sine 35. Is the hypotenuse function angle. Once we have this drawn and calculated, we're done with the angle. We can forget about the angle. That just adds in one little bit, and then we're going to put those values into the XY table. On the left side for x, we have delta x, Vx, and t. On the right side, we have delta y, V naught, Va, and t. And then we'll just calculate the 56 cosine 35. I get 45.87, and 56 sine 35, I get 32.12. $45.87 and 32.12. The initial velocity is up, positive, so acceleration being down is going to be negative. How far away from the ramp does this stunt man land? So in this case, it's asking us for delta x. Delta x is calculated as Vx times time. Looks like we need to know what the time is. In order to calculate time, there's another variable we need to know, because there's got to be 3 knowns in order to calculate for a 4th value on the right side of that table. If initial velocity is 32.12 and it lands at the same height, we know that the final velocity at the end of the projectile motion would be negative 32.12. So now we have 3 knowns, 1 unknown. We're going to use the Votat equation. We've already solved the Votat equation for time. Earlier we said V minus V naught over A is time. So we're going to say negative 32.12 minus 32.12 over negative 10 is our time. So we'd end up with what? Negative 64.24 divided by negative 10, or 6.42 seconds is our time. Well, if our velocity is 45.87 and it maintains that velocity for 6.42 seconds, we're going to multiply those two numbers to determine how far away from the ramp does the stuntman land. What is his range? What is his change in the horizontal position? .49 meters. Question B, how high is the stuntman when he is 35 meters horizontally away from the ramp? So it's asking for delta y at a certain time point, but we don't know what that time point is. Again, when he's 35 meters away, how long did it take him to get 35 meters away? And at that time point, we want to know what his delta y is. So first we need to know how long did it take him to get 35 meters away. So when his delta x is 35 meters and he's traveling at 45.87 meters per second, let's figure out what that time point is. And then based on that time point, we're going to put that time into the y side and figure out what is the vertical displacement at that given time. Delta y over Vx is equal to t. It's just a rearrangement of delta x is equal to Vx times t. And we've got 35 meters divided by that meters per second, 45.87. This will give us our time point. Looks like it takes the stuntman 0.76 seconds to get to that horizontal displacement. And now we're asking ourselves, what is our vertical displacement? What is our delta y at that time point? If we know the initial vertical velocity is 32.12, we know the time is 0.76, we know the acceleration is negative 10, what is the delta y? We're going to be using the equation delta y is equal to v naught t plus 1/2 at squared. We're solving for delta y. The equation's already set up for us, so we can plug in some numbers. V naught is 32.12, and we're going to multiply that by 0.76. And then we're going to add in 1/2 times negative 10 times 0.76 squared. The first part of the equation, I get 24.41. It's really 24.4112. And on the second half of the equation, I would do 0.76 squared, and then half of negative 10, so multiply by 5. So I'm going to take my 24.4112 and I'm going to subtract 2.888. So my delta y, my change in my vertical position for those first 0.76 seconds is 21.52 meters. That's how high the stuntman has gone in that amount of time. Darryl Strawberry hits a baseball with an initial velocity of 40 meters per second at a 60-degree angle relative to the horizontal. So we're going to go ahead and draw that out. We get 40 meters per second going up and to the right, and we need to do the angle at 60 degrees. We know that the horizontal velocity, because it's a velocity triangle, because the hypotenuse is in meters per second, so all the sides will be in meters per second. Our Vx on the bottom would be 40 cosine 60, and our V naught, being the initial vertical velocity, would be 40 sine 60. Once we get those values through our calculator in degree mode, we can put that into our XY table and then forget that the angles ever existed. So he's hitting the ball towards the fence that's 140 meters away, and it's 3 meters tall. We need to determine if the ball is going to go over the fence, hit the fence, fall short. Where is it going to be? So you got to do a little problem solving. Let's figure this out. So if we know how fast the ball is traveling, we could determine how long it would take for it to reach 140 meters, right? If it's traveling at 40 cosine 60, so 40 cosine 60, 40 cosine 60, the ball is traveling at 20 meters per second, and it's going to move for 140 meters. We could then determine what is the time period it would take for it to travel that 140 meters. And then we can see on the y side, what is the vertical displacement, delta y, at that same moment in time. If it's more than 3 meters, it's going to clear the fence. If it's 3 meters to 0 meters, it's going to hit the fence. And if it's less than 0 meters, if it's a negative number, that means it's below ground now. So it's hit the ground prior to getting to the fence. So we need to know the time at delta x equals 140 and then determine the delta y, the height, at that moment in time. Delta x is Vx divided by, or delta x is Vx times t, divide both sides by Vx, and we get delta x over Vx is equal to time. So 140 divided by 20 equals 7. So 7 seconds is the time. It's a long time for that ball to be in the air, but that's pretty cool. The ball's in the air for 7 seconds to reach that 3 meter tall wall or fence or whatever. As far as vertically is concerned, 40 sine 60 gives us a initial vertical velocity of 34.64. We know acceleration's down in the opposite direction, so acceleration's negative 10. Time is 7, and we're looking for delta y. Giving those variables, delta y is equal to v naught t plus 1/2 at squared. V naught would be 34.64, time is 7, plus 1/2 times negative 10 times 7 squared. On the left part, the part that's in the parentheses, 34.64 times 7, I get 242.48, and then I'm going to add to that negative 5 times 49, so 5 times 49. So I get 242.48 minus 245. Ooh, it's a negative number. It looks like it's negative 2.52. So the ball has hit the ground short. It would be underground at this point if it was allowed to move that way. It falls short, it does not go over the fence, doesn't even hit the fence.